Okay, so we will continue with the sixth part of this chapter. We are going to call it dimension, and let's start with the definition of a definition. We'll see a few definitions. Definition. Okay. Okay, let's start with the finite dimensional vector space. A definition about finite dimension vector space. So a vector space is a finite dimensional if it has a basis with only finitely many vectors. So basically, if a vector is a finite dimensional, that means its basis must have finite number of elements. Okay. Number 2, lemma. This lemma says, okay, it is called the exchange lemma. How can we move from one basis to another by exchanging an element of the basis with a vector? Okay, so let me call it exchange lemma. So assume that we have a basis B made or composed with the elements betas, beta 1 till beta n. Okay, is a basis for a vector space, and that for the vector V. Okay, the relationship V equals to C1 beta 1 plus Cn beta n has Ci's different from 0, then exchanging beta I, any beta I for the vector V leads to another basis for the space. So basically, if you have a vector space and we already have a basis for that space, and we have an element, a vector from that space, that can be, of course, be written as a linear combination of the element of the basis. Then if we exchange an element of the basis with the vector v, we will get another basis for the space. Okay. Okay. So let me continue with the following theorem. Number 3. Theorem in any finite dimensional vector space, all bases have the same number of elements. Okay. The lemma we have just seen shows that we can have many bases for a vector space. But what is common to those bases, no matter which basis we have for the space, we will have the same number of elements in that basis and in all other bases for that space. This is very profound because it will lead us to the definition of a dimension. Okay? So, number 4, definition. Okay, so the dimension of a vector space is the number of elements of a vector in any of its bases. Okay, is the number of vectors in any of its bases. Okay, so as I have said, a vector space can have many bases. So we cannot use a basis as a characteristic of a vector space. Since we can have many, we can have more than one. But we can use dimension as a characteristic of a vector space. Because a vector space will have a unique dimension no matter what the basis is. That means no matter what basis we pick for the vector space, that basis is going to have the same number of elements. Any basis we pick for that space will have the same number of elements, the same number of vectors, which is, I think, a very, very beautiful theorem and definition. So let's keep going. Part 5, we have a corollary. Okay. So no linearly independent set can be expressed to make, okay, sorry, any, of course. So we have any linearly independent set can be expressed or expanded to make a basis. We'll see shortly in the tutorial. Keep going with these beautiful theorems and corollaries. 6. We have another corollary. We have any spanning set can be shrunk to a basis. Any spanning set can be shrunk to a basis. And this final. Okay, number 7. Okay, another corollary. Here we have no linearly independent set can have a size greater than the dimension of the enclosed space. Of course, clear. No linearly independent set can have a size, that means the number of vectors in that set, size greater than the dimension of the closed space. Okay, so let's finish this lecture with this last corollary. Okay, we have in an n-dimensional space, a set composed of n vectors is linearly independent if only if it spans the space. In an n-dimensional space, a set composed of n vectors is linearly independent if and only if it spans the space. Okay, so we will stop here, and in the next video we will do the tutorial about dimensions, how to find a basis and how to find the dimension of a space. Is that okay? Thank you.